Hello everyone. This is our first video of chapter 10, where we'll be talking about partial differential equations. And in this chapter, we'll be looking at a couple different particular examples of PDEs that have different physical applications and looking at methods for solving them. So the first example that we have in this section, section 10.2, is the heat equation. And I'm going to direct you to section 10.1 to read about some of the physics of how this equation is derived. But I'm not going to talk about that too much because truly I'm not a physicist and I would just be sort of reading the book out to you. So let's explain. So this is the equation that we've got here. And we see we have our partial derivatives here because we have functions that are of, we have a function that is of two variables. And so I guess first let's say what our u is. So u represents the temperature in a wire. So we're talking about a wire because we only want to deal with one spatial dimension. So temperature of a wire at a point x and a time t. So that means that we've got some wire happening that is of length L, and the temperature is going to be changing over time, of course, and we want to have some model that tells us at any point on this wire, maybe some x, and at some time after now, what's the temperature going to be at any point. So that means that we have x, which is the spatial dimension, and t, which is the time dimension. And again, for reasons that are discussed in 10.1, we have in this equation, we have one time derivative of t, so how it's changing with respect to time. That makes a lot of sense. And then we actually have two spatial derivatives of u. So we have to take the derivative of u twice with respect to x, so how it's changing sort of in space. If we had more than one spatial dimension, like if we were modeling the heat on a surface, so then we would have two spatial dimensions, or in a room, and we'd have three, then we actually would take two derivatives in each spatial dimension, and then you add them all together. But again, that's discussed in section 10.1. Now, if we had more than one spatial dimension, like if we were modeling the heat on a surface with two dimensions or in a room with three dimensions, then we would have two spatial derivatives in each dimension, and then you sort of add them all together. And you can see that in section 10.1. Now we have a couple of other terms here. We have this beta, which is the diffusivity of the material. So sort of how well it conducts heat and that sort of thing. And then P is going to represent the heat from outside sources. Because of course it matters if the room we're sitting in is hot or cold and that sort of thing. Now the last thing that we need to have a model here are our initial conditions. And we have two different types here. One, we actually have what we call boundary conditions, because it's what is happening in the spatial edges of our wire. So when x equals 0, that's our first point, or one boundary point here, for whatever time. And then our u at our other endpoint And we're going to say those are both 0. So that's like if we're holding the ends of our wire at 0 degrees Celsius. And this could be anything. It could have t's in it because it could change over time. And then finally, we need actual initial conditions, the way that we're sort of used to, which is what is happening when t equals 0. And this is going to be some function of x. So for right now, we're going to assume that p is 0, that we don't have any outside heat sources, so that we just have our wire sitting in a vacuum. And then we can put everything all together and get this problem. There it is. There's everything all together. And so we're going to call this an initial boundary value problem. And we have the first equation models everything that's sort of in the middle of the wire and for positive time. The second condition is telling you what's happening on the boundary of the wire. And then the third condition is telling you what's happening at the very beginning. And so this is in one particular form of the heat equation. Okay, and so this is one of the most famous partial differential equations, which is, why it's the very first thing in this chapter. Okay, so now's the fun part. We want to solve this equation. So our strategy here is going to guess that the solution looks like, so the solution that we're looking for is our u of xt, and it would be kind of nice if it had a form where it was some function of x, something with just the spatial information, times a function of t. So I'm going to guess that we have something that looks like a of x times b of x. And this approach is called separation of variables. So now the reason that we do this is that now that if our function is separable like this, then we can compute our partial derivatives really easily. So we can see that du dt is just going to equal, this is derivative with respect to t, so we leave the a of x alone, and we get a b prime of t. And our second derivative, our d2u dx squared, equals a double prime of x times b of t. So putting everything together into the first line of our initial boundary value problem, we get a of x, b prime of t equals beta a double prime of x, b of t. Now we do what we do with our separable equations back from the beginning of this class, and we put all the t's on one side and all the x's on the other, and we get b prime of t over beta b of t equals a double prime of x over a of x. Now let's say we fix time t, then the left-hand side will just be a constant because we've plugged something in for t. And so no matter what x is, that now the quantity on the right-hand side will have to be a constant as well because it's equal to the left-hand side. So this equality must also equal some constant. And just by convention, we call this constant a negative, and we say negative lambda. So this set of equalities is going to give us two more equations. We'll just rewrite the left-hand side equal to negative lambda, and then what's now the middle equal to negative lambda. And we get, let's scoot up some room, we'll get two ordinary differential equations. So one in x, a double prime of x equals negative lambda a of x, and one in t, b prime of t equals negative lambda beta b of t. Now let's think about our boundary conditions on x. We have u of 0t equals a of 0 times b of t equals 0, and for our other endpoint L, u of L of t is going to equal a L times b of t equals 0. And this is going to have to happen for all t. So if a of 0 and a of L are not 0, then that will make b of t, and by extension u of xt, equal identically to 0. So what we get is either u of xt is identically equal to 0, or a of 0 and a of L both equal to 0. So when u is identically equal to 0, this is we call this a trivial solution. And we don't really want to worry about those right now. So assuming that we don't have the trivial solution, then we get a of 0 and a of L equals 0, and this gives us a boundary value problem just in x. So we have a double prime of x equals negative lambda a of x, and we have our boundary conditions a of 0 equals a of L equals 0. So this is a lot like the initial value problems that we have seen. So this is a second order ordinary differential equation. It's even linear with constant coefficients. It's fairly easy to deal with. And instead of, now we're talking our one dimension is a spatial dimension instead of a time dimension. So instead of knowing what the function's value is at the starting time and then the derivative at the starting time, we have two conditions on what's happening at either end. So that's in a time, when we're talking about time, we can't really talk about either end because there's no end to the time. So sometimes you just have things set up a little bit differently. But all the theory that we have about solving these types of equations is still going to hold. So now the question that we have is, what values of lambda will give us non-trivial solutions to this? Because as we've seen, if a of x, or if u of x, but in this case, if we have a of x equals 0, that will be a solution to this because of our boundary conditions. So depending on what lambda is, we may or may not be able to find non-trivial solutions, and that's what we'd like to figure out next. So like I said, this is a second order linear differential equation with constant coefficients. And so we can find the characteristic equation. Which, if we move the lambda term over to the left-hand side, we get r squared plus lambda equals 0. And how to solve this and how to get solutions from this is going to depend on what lambda is. So case 1, lambda negative. If lambda is negative, then we get real distinct roots in this case. So we get r equals plus or minus the square root of negative lambda. And then our solutions, let's write it in blue, we get a of x equals c1 e to the square root of negative lambda x plus c2 e to the negative square root of negative lambda x. And now we can plug in the boundary conditions. And we get a of 0 equals c1 plus c2 equals 0. And plugging in L, we get a of L equals c1 e to the square root of negative lambda L plus c2 e to the negative lambda L. And this equals 0. So let's multiply through by e to the square root of negative lambda L and replace c2 with negative c1. And that gives us c1 e to the 2 square root of negative lambda L. This second term, the c2 e to the negative stuff, the e's will cancel out. And so we'll just have c2, and then we'll replace that with negative c1. And we can pull out the c1, and we get e to the 2 square root of negative lambda L minus 1, and all of that equals 0. Now, switch to green. This thing is positive. It's not 0. And the way you can tell that is if you think about an exponential function. Let's see, e to the z, that's 1. The stuff in the exponent is positive because our L is positive and negative lambda is positive. And so we will have to be, 2 times the square root of negative lambda L is somewhere on the right-hand side here. And so we'll have to be above 1. And then when we subtract 1, we're above 0. So anyway, what that tells us is that C1 and then, of course, C2 have to equal 0. And then let's change this to blue. If C1 and C2 equal 0, then A of X has to equal 0. And so this is a trivial solution. Okay. So the point here is that in case 1, where lambda is negative, we only get trivial solutions. Okay, so case 2 is going to be where lambda equals 0. And then you have a repeated root. So R is going to equal, remember what our characteristic equation was. If lambda equals 0, then our characteristic equation is R squared equals 0. And so R equals 0. And then the solutions that we get one solution, which is C1 times e to the 0, which is just C1. And then to get another independent solution, we remember we have to multiply this by an x. And so we get C2x times e to the 0. And so this is the form of our equation, or rather of our solutions. And again, if we plug in the boundary values you can verify this yourself. So the boundary values imply that, again, a of x has to be 0. So again, we only have trivial solutions. In case 2, only get trivial solutions. Okay, so we've been looking for the values of lambda that give us non-trivial solutions, and we haven't found any yet. So let's go on to case 3. Case 3, lambda is positive. That's our last case. And then our r will equal plus or minus the square root of negative lambda, which, because lambda is positive and negative lambda will be negative, what we get are plus or minus I square root of lambda. So we have complex roots. And now our solutions are going to have cosines and sines in them, like we've seen. So our a of x will equal c1 cosine square root of lambda x plus c2 sine square root of lambda x. Okay, time to do the boundary conditions again. So let's see, a of 0 equals 0 will give us that, let's see, the sine term will go away, and so then we get c1 cosine of 0, which is 1 equals 0, so then c1 equals 0. And a of L equals 0 will imply c2 sine of square root of lambda L equals 0. So if c2 equals 0, then it's a trivial solution. And so in order to get, let's see, the only non-trivial solutions will happen if the sine term is 0. So sine of square root of lambda L equals 0, which will happen if square root of lambda L equals n pi for n equals 1, 2, 3, etc. And so switch to blue. Now we can sort of solve for lambda, and we get lambda equals n pi over L quantity squared for some natural number, 1, 2, 3, etc. So we only get non-trivial solutions for these lambdas. So these values of lambda are really special for the heat equation that we are trying to solve, because they're the only, they're the numbers that are gonna sort of help us find non-trivial solutions. And so these values of lambda, these lambda are called the eigenvalues for the problem. And the corresponding solutions, which of course are, so remember up here our solution was looking like C1 cosine plus C2 sine, but our C1 is 0, and our C2 is still going to be something. So that means that let's get back here, our A of X equals, now instead of writing C2, I'm going to write AN times sine of n pi x over L. And that n pi x over L came from up here. So when we plug in our n pi over L squared in for lambda. And so these functions are the eigenfunctions. And in this case, our AN are non-zero constants. Okay, now we've got one more thing to do. We can go back to the t equation, or the b equation, however you want to phrase it. So we get b prime of t plus beta, and now instead of lambda, we know what lambda looks like. So we've got n pi over L squared times b of t equals 0. And this is just a first order equation. We get b prime equals some constant times b. So b is going to have to be an exponential function. And it will look like, depending on what n is, we get the solution bn of t equals little bn e to the negative beta times n pi over L squared times t. And so we have a solution for each n. Now, that gives us a solution un of xt for each n, which equals an times bn. And we can combine the constants little a and little b into a single one when we multiply them together. So we get Cn e to the negative beta n pi over L squared t times sine of n pi x over L. So now each un is a solution to the heat equation with the boundary condition. So the boundary condition is u of 0t equals u of L of t equals 0, but not the initial condition u of x0 equals f of x. Okay, we haven't plugged that u of x0 equals f of x in yet. But we have a bunch of candidate solutions. In fact, we found the only possible non-trivial solutions that can at least satisfy the boundary conditions. Those UNs, or let's see, as are any linear combination of UNs. Because we can multiply those UNs by constants and then we can add a bunch of them together and they'll still be a solution because of the linearity of our heat equation. So now this video is getting pretty long, and so I'm going to do an example of how you use this and how you actually solve the initial conditions in our next video. Example in next video. All right, and I'll see you then.